Okay, so welcome back to another video. So here we have an improper integral from 1 to infinity of 4 times the floor of x divided by x to the 5th power dx. So you can guess from the thumbnail that the value of this integral is actually a special value of a special function that we'll be utilizing. So this is actually not that bad of an integral to solve, since all you need to do is just utilize the definition of the floor functions. As you can see from past videos I did with floor functions integral, that we are actually going to convert this into a sum of integrals. And that pretty much is the takeaway from there. And for a little bit of fun with that special value, we're actually going to verify / evaluate that special value instead of just treating it like it's a given. So it just adds a little more fun to the mix, because why not? So anyway, let's actually just jump right in. So by definition of the floor function, we could say that the floor of x is equal to k, such that x is in between the following interval of k inclusive to k plus 1 non-inclusive, and that's of course for k is actually an integer. So utilizing this, and we'll call this integral capital I, and for 1 I can factor out the constant 4 outside of that. So we have 1 to infinity of the floor of x, and then divided by x to the power 5 dx. Then utilizing that definition, and of course we can create this as terms of sums. So this will be 4 times our infinite sum, starting with k is equal to 1, and then the integral starting with k and then all the way up to k plus 1. So we're building each step at a time. Then put this back for k and then divided by x to the power 5 and then dx. Pretty simple from here to see that evaluating this. So we have 4 then times the infinite sum. K is equal to 1. So this will yield us negative k divided by 4. That's just simply factoring out the constant k. And then now multiply with after performing the integration, it's just 1 divided by x to the power 4. And then evaluate this from k plus 1, or rather k, to k plus 1. And then simply putting everything together, so the 4's will cancel, so that's nice. And then now put it in for our bound, so we'll now have the following infinite sum. So from infinity, and then k equals 1, so this will yield us k divided by 4. I'll save the simplification for later, so we'll just leave it the way it is for now. And then minus k divided by k plus 1 to the power 4, right? So now this just leaves us to evaluate what's inside of our sum over here. So let's actually do a little bit more observation. So we note the following. So k divided by k to the power 4, then subtract k divided by k plus 1 to the power 4. So we can actually do a little bit of some simplifying. For 1, as mentioned, k divided by k plus k over 4, that's just 1 divided by k cubed. And then we can actually fix the numerator for our k plus 1 to the power 4 denominator. I can write this as the same thing as k plus 1 subtract 1, and then divided by k plus 1 to the power 4. Then simply we can actually break this up with using even more linearity with fractions, yielding us with, we'll write this over here, 1 divided by k cubed, then subtract 1 divided by k plus 1 to the power 3, and then add this with 1 divided by k plus 1 to the power 4. Okay, and so now we can actually just put this back into our infinite sum substitution over here to make the simplification even more easier. So now putting this back, so we have 1 divided by k cubed, then minus 1 divided by k plus 1, then cube, and then add this with 1 divided by k plus 1 to the power 4. Okay, and so now this makes things a little bit easier. So how do we actually proceed forward here? Well, again, I can actually now break this up into a difference of sums using linearity again. So we'll now have the infinite sum of 3 different fractions. So that leaves us with 1 divided by k cubed, then subtract the infinite sum of k equals 1 of 1 divided by k plus 1 cubed, and then add this with our infinite sum, and k is equal 1 of 1 divided by k plus 1 then to the power 4. Then we can actually take a look at each of these fractions one at a time. So let's start with that. Thing is that we don't really need to worry about our first sum that we're dealing with. Instead, what we want to do is pay attention to the other 2 sums, and you'll see what I'm coming from in here. So first, let's notice for 1 divided by k plus 1, then cube. So what we're going to do here is we're actually going to do a little bit of re-indexing. So I can actually change this up, starting that our index is going to be k is equal to 2, and then I'll put us at 1 divided by k cubed. But to make the equivalence true, in other words, I can actually write this as the same thing. So the infinite sum at k is equal 1 of 1 divided by k over 3, but we have to evaluate this for the k equals 1 term. So doing so, then that means I'll have to subtract 1. So a new substitution we could put in for later, and then next we'll do the same thing for this other infinite sum over here. So k is equal 1 of 1 divided by k plus 1 to the power 4. In other words, do the same thing. So now instead we'll have our index start at k is equal to 2, and that'll put us at 1 divided by k to the power 4. Doing that same process again, so we'll have to put this back at k is equal 1 of our same series over here, but except we have to evaluate at the k equals 1 term. So k equals 1 of 1 divided by k to the power 4. Then again, evaluate this, that's still 1, so subtract that, so it's minus 1. Then put this everything back together, so I is indeed just equal to the infinite sum of k is equal 1 of 1 divided by k cubed. Then subtract, so new substitution over here, this is the infinite sum, k is equal 1 of 1 divided by k cubed. Then subtract 1. And then now add this with the new substitution, the infinite sum of k is equal 1 of 1 divided by k to the power 4, and then subtract 1. And what's nice is we're going to have some terms that cancel, so the series for 1 divided by k to the power 3 is going to cancel, and then we have the 1's now cancel, so pretty much all that's left now is just that this is the infinite sum of k is equal 1 of 1 divided by k to the power 4. And greatly enough that by definition, this is the same thing as written as the Riemann zeta of 4, and then of course to extend this even further, let's actually now calculate what that value of Riemann zeta of 4 is, despite, I'm sure you can look this up to know that what that value is exactly, but let's actually go into a little further detail of that. So as you can already guess, the Riemann zeta of 4 is actually just equal to pi to the power 4 divided by 90. But how do we get such a value with that? So there's actually several ways to prove the Riemann zeta of 4 is equal to pi to the power 4 divided by 90. So for 1, rather 2, you can actually use the Fourier series of x to the power 4 or x squared. Another way you can use this is utilizing Bernoulli's numbers after putting in for the Riemann zeta function at the even integers. And another way you can do this is by using the multiplication table for the products for the Riemann zeta of 2, square that. And you'll notice that from that table, the diagonal entries of that multiplication actually adds up to the sum of giving you Riemann zeta of 4. So we're actually going to stick with a more easier one, and I'll just use the Fourier series of x to the power 4. So what x to the power 4 in terms of its series representation for, of course, in the interval, the closed interval from negative pi to pi, is that x to the power 4 is equivalent to pi to the power 4 divided by 5. And of course, all this is an easy calculation to verify using that definition of the Fourier series. Then we have plus the infinite sum from n is equal 1 of 8 times n squared, then times pi squared, subtract 48, then divided by n to the power 4, multiplied by cosine of n pi, and then multiplied by cosine of n times x. So letting pi equals x, so substituting this back in, so that means that'll give us pi to the power 4 is equal to pi to the power 4 divided by 5, and then add this with our infinite sum, n is equal 1 of 8 times n squared pi squared, then subtract 48 divided by n to the power 4, and then that'll give us cosine square of n times pi. This can actually completely vanish since this is equal to 1 because of n is equal to 1, that's cosine of pi, and it's always going to yield us between either -1 or +1 depending on what our natural number n is, but square that, it's always going to be a +1. So continuing forward, I'll subtract a pi to the 4 divided by 5 to both sides and split this splitting this with the linearity. So that'll give us 4 times pi to the 4 divided by 5, so equal the infinite sum at n is equal 1 of 8 times n squared pi squared divided by n to the power 4. Then subtract the infinite sum of, starting with n is equal to 1, of 48 divided by n to the power 4. And then I can actually factor out the 4 from both of these sums and then divide that both sides, so I'll just cancel out the 4 from the numerator, so pi to the power 4, then divided by 5. And then factor this out, then that cancel the n squared and from the top and just leave it with an n squared on the bottom, yielding us now with just 2 pi squared multiplied with the infinite sum, n is equal 1 of 1 divided by n squared, and then subtract now 12 times the infinite sum, and n is equal 1 of 1 divided by n to the power 4. And so we know that 1 divided by n squared, Basel's problem, is pi squared divided by 6. That'll be just yielding us pi to the 4th, then divided by 3, and then subtract this with 12 times the infinite sum, n is equal 1 of 1 divided by n to the power 4. Then I can just now subtract, or rather, I can actually just add this to the other side, do a little bit of reversal. And so doing so will yield us that 12 then times the infinite sum of n equals 1 of 1 divided by n to the power 4 is indeed just going to yield us with pi over 4 divided by 3 minus pi over 4 divided by 5, aka 2 pi to the 4th divided by 15, and then just divide the 12 to both sides and simplify. And so therefore that the Riemann zeta of 4, which is equal to the infinite sum at n is equal 1 of 1 divided by n over 4, is indeed just equal to pi to the power 4 divided by 90. And so therefore that is our final answer. Just to go back over here, that it is pi to the power 4 divided by 90. A special value for the Riemann zeta of 4 and a special value for this integral dealing with the floor function, just like that. So yeah, that's pretty cool if you ask me.